Alright, let's take a look at imaginary numbers. Before we do that though, a little quick history. There was a time when even 0 was not accepted to be a number. Um, you believe that 0 is a number, condemned a witch, and put the concrete shoes on, drown in a lake. Uh, as time rolled on, 0 was accepted. Mathematicians and philosophers agreed to accept it, and then you know numbers came along such as the square root of 2, and Pythagoras especially, he ran this cult, and you could not be accepted in this cult. In fact, he would condemn you to death if you try to bring up some number such as square root of 2, when these days we know it's just a number somewhere in between 1 and 2. Time rolls on, and eventually, we find out numbers such as pi or negatives, for instance, and now we have this I, right? What I represents is the square root of a negative number. 1i is square root of negative 1, since square root of 1 is 1, and with that negative we call it an imaginary. Now, where did this come from? It started with trying to find a solution if we ended with an equation such as this: x squared equals negative 1. Right, so now we can solve this. We know it's imaginary because when we take the square root to get x by itself, remember, anytime you do a square root with a variable, you have to have that plus minus. So the solutions to x squared equals negative 1, this here is x is a positive or a negative I. Alright, a little background about the imaginary number and where it came from. That's why we need it, how we need it, and it's used in many applications these days. So, first off, I would like to point out, it's not a real number, right? Real numbers were everything such as the first 4 I gave, but I is not a real number. Now, the arithmetic, the algebra behind I is pretty simple, actually. If we had 2 plus I, let's say, first off, we call this a complex number because it has a real part. This 2 is real, but this I is imaginary, and therefore we call it a complex number. We cannot combine 2 plus I. It is not 2i. It is done. 2 plus I is it. So let's take this example. Alright, if we had, let's say, 2 plus 3i, I'm going to group these. This is pretty common, just to show that we do in fact have 2 complex numbers that we are adding, or in this case subtracting. And off to the side, I want to point out operations with imaginary numbers are very similar, like as if you just had variables. If I change this to 2 plus 3x minus negative 3 minus x, right, what we would do is distribute this negative, and ultimately parentheses aren't really needed, plus 3 and plus x, right, after getting rid of the parentheses. And then we combine like terms. 2 plus 3 is 5, 3x and 1x is 4x. Well, imaginaries work much the same. When you distribute this negative to clear the parentheses, and then we're left with 2 plus 3i and plus 3 plus I. And just as we combined variables, we combine like terms with imaginary numbers. we have 2 and 3 is 5, and 3i and 1i is 4i. Pretty simple, right? Just like we combine variables, we can combine imaginaries. One difference, however, if I had x, I could only combine it with like terms with x's, x squareds with x squareds, and cubes with cubes. However, with imaginaries, if I have an I, really I can't do anything. But beyond that, let's take I squared for instance. Any power of I we can simplify. Right? If I is the square root of -1, then I squared would be the square root of -1 squared, and square root and a square cancel, and therefore I squared is simply -1. What about I cubed? Well, if we take I cubed and represent it as I squared multiplied by I, since we add exponents, right? I squared was -1, so we multiply that by another I, and we have -I. Therefore, I cubed is the same thing as -I. I squared, same thing as -1. I, we simply leave. Let's investigate I to the fourth. Well, I to the fourth we could represent as I squared multiplied by I squared. But again, I squared we knew is -1, right? So -1 multiplied by another -1 is +1. Therefore, I to the fourth, +1. Well, thankfully, once we get I to the fifth, this pattern keeps repeating, because notice I to the fifth, come on pen, there we go, is just I to the fourth multiplied by one more I, and I to the fourth, as we just found, is 1, so we have 1 times I. Jeez, my pen is acting up, sorry. Whatever. Right, and we're back to I. So recognizing this pattern, we could do I, and then I squared is -1, I cubed is -I to the fourth is 1, right down here at I to the fourth, and then it repeats, I to the fifth, I to the sixth, I to the seventh, I to the eighth. Every 4 we arrive back at, every fourth power we arrive back at 1. Okay, so we could use that pattern to find any power of I. The last thing I want to point out with imaginary numbers is a canceling mistake. That's pretty common if they were variables, right? If I change this to just x's, just as before, come on, it's not liking me to change colors, so apologize. Just as before, we cannot cancel x's, right? We can't do that. Because we have plus. If this were all multiply, we could. Well, same thing here. We cannot cancel these i's. It's a common mistake. If I ended with an answer 2 plus 3i over -3 minus I, that is it. There is no more simplifying that we could do.